hopefully finish up 2 more chapters in these 2 weeks, right? Let's hop back to the lecture. No, oops, that's the wrong one. 33. Okay, scroll up, scroll up, scroll up. Okay, yeah. So, well, today's May 2nd, right? So we're starting off chapter 33 today. And the hope is that, actually, what I'm hoping for is actually kind of complete the lecture part by this week. And that way we can do there's going to be a worksheet either today or tomorrow. Actually, this is actually shifted over. And then we'll do another worksheet on the Michelson interferometer after the midterm. And so the midterm is on Monday, right? Next Monday is the midterm. I posted all of the lecture notes, all the lecture videos, and all the worksheets, and also made a discussion for you to give me feedback on which problems you want me to kind of go over for the midterm review video, right? Unfortunately, we're not going to dedicate a class period to that, right? But you can watch that because I made it due on Thursday night. So I'm going to make the video on Friday, and then so hopefully you can actually watch it on Saturday and Sunday, okay? It's just me going over a few example problems. You know, I may just even do more than one problem per chapter because I have unlimited time on Canvas, right? So we'll see how that turns out. So that may be a better model going forward, right? Because then I'm not limited to just doing one problem per chapter. Okay. Any questions about the midterm before we get started today on chapter 33? Actually, before we get started on chapter 33, I sent an email out over the weekend about this already, actually. We're doing a tour of the National Ignition Facilities, which is this thing here. So, you know, a person is about this tall. Imagine a giant sphere where you have 300 lasers pointing at it. And these are like high-power megajoule level type of lasers that will just burn holes into walls. And what they do with this is basically ignite fusion with it. And you might have heard a little bit about this on the news last December. They were actually able to generate more energy than they put in, technically. It doesn't account for all the laser energy, all the inefficient in the laser. But it is a milestone for the world to be able to generate power from fusion energy as opposed to, you know, burning fossil fuel or the other version of nuclear reaction, right, which is fission, where you're splitting the atom up, where fusion is actually you're combining atoms together to release energy. So that's gonna be on May 18th. We're gonna leave Turlock at about 2 p.m. So we'll figure out how some sort of carpool situation, and we'll probably be returning about 8. So that's that entire afternoon basically. So if you have a final, for example, at that time, unfortunately, that will preclude you. Okay. So the National Ignition Facility is actually funded by the National Nuclear Security Agency, which also funds my research in neutrino physics here. So we have a direct link to the agency that funds this. What you need to go is you need some sort of government issue ID, right? And then just email me your name that's on the ID, actually, so your ID name has to match. The name you give me has to match exactly what's on your ID, okay? And assume, since you're going to email me, I will know your email address and the country of your citizenship, because if you're not from the US, they do extra background checks on you, so. Okay, so if you're anyone's interested, let me know. Just email me or just talk to me after class. Okie doke. So, chapter 33. Finally, optics. All right, you guys already done all the labs on optics, so you know everything about optics already, right? We're all good? Okay, check. No lecture needed. All right, let's go through the little bit of math and relate what we just learned from chapter 31, which is electromagnetic waves, right? And you should think about optics as just a way to study light, right? Or control light. For example, controlling 300 lasers to make fusion happen, right? This is all about optics. So like 99% of what they spend money on is actually on controlling light, which is known as optics. Okay. Specifically on chapter 33, we're going to talk about wave optics, which is actually Well, let's talk a little bit about that, right? Like last chapter, well, chapter 31, we called it the last chapter because we just wrapped that up, right? We know that light is actually electromagnetic waves, right? We can write the wave equations for the electric field and the magnetic field on an electromagnetic wave, right? The electric field, is perpendicular to the magnetic field, right? And these waves propagate forward in the third perpendicular axis, right? Using the pointing vector, right? So if the electric field is pointing this way, magnetic field is pointing this way, the wave will propagate forward following this thing called pointing vector, usually with the symbol S, okay? Right? And this chapter, we're going to study how we can treat light as purely a wave phenomenon, meaning we're going to go back to the stuff we learned in chapter 17, right? So in case you want to, a lot of the equations that we'll be using will come from chapter 17. When we first learn about waves, for example, if you just, so this is a little crest of water wave just passing through a narrow gap, right? What happened is that it creates these these pattern. These are known as circular wave patterns that's going outward like this. Okay, so this chapter will be dedicated on how we can actually utilize this phenomenon, the wave nature of light, in order to make different measurements or or create fusion. And the other way to actually treat light is actually, don't think about it as electric field and magnetic field oscillating as waves up and down. Just treat it as just a pointing vector going straight forward. So this is known as the ray treatment of light, which is what we're going to cover in chapter 34. Okay, that's going to be next chapter. Hopefully we'll get to some of it. Okay. And you may think, well, is light a wave or a ray, right? And this has been an argument since the 1700s when first people started playing around with light. In reality, it's actually both. Okay. And those of you who are interested in learning more about how you can actually treat both of these things, both the wave and the ray, the wave and the ray nature of light at the same time, right? You're welcome to register for the next class, which is the third semester of called Modern Physics, which is actually physics of the. It's kind of old now, actually, to call it modern physics. It's the physics of the 20th century, which is 1900s, 1905, basically, when Einstein first discovered special relativity, up to now. It gets even weirder. Okay, so I'm going to show you this little experiment that I did as an undergraduate, like you guys, where we have a laser, right, that's basically sending light at a wavelength of 400 nanometers, okay, right? And there's some mirrors and stuff like that. We don't need to worry about the mirrors, okay? And this little thing called BBO crystal is known as a down conversion crystal. It actually converts this light to two lower energy photon beams of light, okay? And what happened is that you can send this light down this little tube. So if the one for the left, right, is horizontally polarized, right? Remember we just learned about polarization. The one on the right is going to be vertically polarized. They will always have opposite polarization, right? And it's a conservation of angular momentum situation. Okay. So what happened is that if you send this down some fiber that has some length to it, right? This will be a short fiber optic cable, and then you detect this light, right, as horizontal. Okay. What happened is that you can make a longer cable, so there's some delay, right? So you can actually, tell Bob, well, this is going to be measured by Alice. Alice say, oh, I measure this light to be horizontal. You can actually tell Bob that, oh, the light you're going to measure is actually going to be vertical right away, okay? But let's say, right, the next beam, next part of the light that comes out, right, is vertical, right? We know right away if Alice measures vertical, the next point that Bob is going to get is going to be horizontal, right? And then, H, V, whatever that is, right? And you can assign these things, right? Let's say we make H 0, and then V 1, and then 0, 1. You can see how that is actually a way to transmit information right, without making copies of it, okay? Because the way we send information right now is basically making copies and copies of it and just sending it out to the world, encrypting it, right? That way no one else can see our information. But in this situation, right, if we have if we were measuring ones and zeros here, the other side will always have this defined state so that you actually have the information on the other side also, if that makes sense, okay? And the weird thing is that, well, if you don't have, if Alice is not telling Bob what was gonna come out on the other side, right, it's just gonna get random stuff instead, okay? And this is an interesting way to pass information along. And this is known as a study called quantum information. Quantum information science. I think they usually like to call it science and technology, right? This is QIST, okay? And this is basically the stuff I did when I was an undergraduate at Santa Barbara, playing around with these sensors so we can actually detect these vertically versus horizontally polarized light, okay? As I mentioned, right, light has, what we're going to do this chapter, we're going to take care of study the wave model of light, where we treat them as waves, okay? Next chapter, we're going to treat them as rays. In reality, you actually need to treat them as what's called photons, which is basically a combination of the two, where it's a little packet of wave that has a certain width, okay? So they're little quantized little packets of stuff, okay? And that's what, in reality, light is, okay? So since we're going to treat light as waves, so let's review our wave stuff from chapter 17. You can tell from the figure here, right? I grabbed this figure from chapter 17, okay? Remember when we had sound waves, when we played around with sound waves, what happened is that if you have a speaker playing a sound, it'll create a wave, right? That's going to be going outward. And you can place a second speaker like at some point behind it, where either the crest of the second speaker will align with the crest of the first speaker, or they could be anti-aligned, so you can actually create these things called noise canceling headphones, right? So we're going to utilize this in order to see when things will be constructively interfering, right? Hopefully you remember that phrase ring a bell, right? And destructively interfering, okay? Destructively interfering, okay? And it's very important because one interference will give you a big boost in the signal. The other one will basically just cancel out the signal you will see, right? Okay? So let's do this in 2-dimension, and this requires a little demo from PHET. So let's load that. Ooh, it works this time. I don't have to open a browser. Maybe it works. It's still loading. Come on. Yeah. Okay. So what we're going to do is we're going to look at how interference happen on a 2-dimensional plane instead. Okay. In this little simulation, what we're going to do is we're going to just have water waves, right? We're going to drip water down here, and this creates a little ripple of waves that goes out. You can even do this at the pond here. Just throw 2 rocks out into the pond, and then you'll see these ripples. Okay. So what I'm going to do is turn on both of the faucets, right? And what happened is that, right, the dark area is where the wave is at the lowest point. The blue area is when the crests are lining up with each other, right? So you can see that, right, as these wave propagates out, at some angle, right, it creates these blue spots, right? Especially actually the one that's going straight to the right, right? That's making these bright blue spots. You can see a line here, right, where there's always basically no blue. It's not blue or black, right? Right? These are the part that are destructively interfering all the time. This is the part that's constructively interfering those 2 waves all the time, okay? So hopefully that makes it a little bit easier to picture compared to so if you just follow this line here, right, it's basically the same thing as the speaker, right? But then in 2-dimension, you have these other lines that can also create destructive and constructive interference also. So it's just a more complicated situation, okay? And speaking of complicated situation, if we go over here, right, this is going to be the still drawing of what's happening over there. So it's really hard to see this, right? Okay, so we're going to go through this picture slowly, right? So these little stars here, green star and blue star, right? These are the little drops of water that we're placing into it, right? So the drop of water lands here, and then, right, the green wave propagates outward in these concentric circles, right? The blue wave propagates outward along these concentric circles also, okay? And there's all these complicated lines around, but let's just focus on maybe one particular line, right? Let's focus on maybe this line, this orange, where I'm highlighting orange, right? So along this line here, what happened is that while sometimes the crests, the green crest and the blue crest will run into each other, so they will actually constructively interfere, right? At some point, they will destructively interfere, right? Constructive, destructive, constructive, destructive, constructive, destructive, right? Okay, right? So that's how you can see it along this vertical axis, okay? What we're going to do, we're going to actually study how this effect propagates outward horizontally like this, okay? Actually, we don't even need to look at the stuff on the right, okay? We're just going to look at the highlighted yellow area, okay? Okay. If we look at that part, right, so the green ring goes out here, right, and then it runs into the blue one here. Unfortunately, my highlighter actually changes the color, so they both look green. Okay, so let's erase that, right? So at this point, right, this is a constructive interference, right, where the two rings, the two crests of the waves are running into each other, right? So you get a wave that's twice as big. Okay, same thing here, same thing here, same thing here. Okay, so these are the points. Okay, I'm going to mark this in purple. Okay, purple, 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 right? Purple are the constructive interference point. Okay, okay, right, okay. Along here, right, where along this black line here, right, what happened is that the green is, this point is halfway between the two crests of the green side, right? So halfway between the two crests is actually the trough, right? So the trough is running into the crest of the blue. So what happens at those points? You guys remember? Then you basically get zero, right? So this is basically the destructive interference point. Okay. Yeah. Right. These are the destructive interference point. Okay. You can also actually see this in the simulation if it's still running, right? Oh, it stopped. Okay. Okay. So you can see that this line happens, right? This is the destructive interference line. This is the constructive interference line. Okay. You can see that just by drawing these circles. Okay. Right. So what we're going to do is we're going to see that, well, along here, if we place, let's say this is light propagating outward, right? If we put a screen here, right, this is going to create a bright spot, right? And this is going to create a dark spot, okay? And this is going to be known as an interference pattern that's on the little screen, okay? Okay. So what we're going to do is figure out that, well, how do I figure out where these points are, right? Okay. So in the constructive interference line, right, along this purple line, right, the difference in the distance that the wave travel is exactly one wavelength of the wave. Okay. Okay. Where the destructive part is they're exactly one half of a wavelength apart, right? It's very similar to the speaker situation where, right, up here, right, if you place the speaker one wavelength behind the other one, right, you always get constructive interference, right? So they will amplify each other. If you place the speaker one half of a wavelength behind the other one, you'll always get destructive interference, right? So this delta R is really quantifying for us, right, whether or not we're going to get constructive or destructive, right? So if delta R is some integer value of lambda, we get constructive. If delta R is half integer times lambda, then we actually get destructive. So that's the important point of this kind of picture here, okay? So any questions about this before I move on? All right, so that's an important point, okay? So delta R, right, if it's, you know, maybe some integer multiplied by lambda, then we get constructive, right? If we get delta R that is 1/2 times some integer, maybe like 1, 2, 3 times lambda, then we get destructive, okay? So that's an important point on this diagram. All right, well, sorry, I guess they both wrote it down also, okay? What we're gonna do now is we're gonna jump to how light behaves, right? So all of this can be done with just water waves, right? You can see this physically. You can also see this with light. This is known as the Young double slit experiment. So let's do the PHET simulation again. You gotta load it again, or yeah. Just gonna play around with it. Learn a little bit more about interference. So instead of water waves, we're gonna put them with slits. Okay, I'm gonna do a 2-slit thing. Okay, place the slit maybe closer. Is there a way to do that? Okay, it doesn't actually matter. And then I start the waves. Okay. So what's happening here is you just have some wave they're known as plane waves. Okay, they just look like just kind of water cresting over, right? Or you can think about it as the electric field amplitude going up and down, up and down, up and down, right? Okay, as it goes along here. So similarly here, right, we have some lines that are never like a bright spot, right? Right, the similar way we had when we had the water, right? We have some lines that are always giving us the bright spots, right? Okay. So what happened is that, can I put a screen here too? Guess not. It's okay. So we're going to see this picture next here, where, right, when we have these light electromagnetic fields impinging on basically two little holes, right? Sometimes you would get a bright spot, sometimes you would get a dark spot, and then they oscillate between bright, dark, bright, dark, bright, dark, bright, dark. It gets a little bit fainter further away you are, but you have this pattern still, right? Where, right, the bright spot comes from the fact that these are lines that are giving you constructive interference. The dark spot is where they always have destructive interference, right? No matter how far the screen is, right, as long as you're on this line, you're going to have constructive. If you're always halfway between these lines, you're going to have destructive, right? Okay. So this is known as the Young double slit experiment because of some guy named Young in the late 1800s did this with not lasers, but like with candle lights and stuff like that. It was really hard back then to do this sort of stuff. Okay, so let's start off with a little question, right? So let's say if we move this viewing screen closer, right, what will happen to these fringes? Okay, so sorry, these bright dark stuff is called fringes, right? Okay, what would happen to them? Okay, do they A, get brighter but otherwise don't change? Okay, would the fringes get brighter and closer together? Okay, or would they get brighter and further apart? They will spread apart. Okay, okay, or they would just get fuzzy. Okay, or they just disappear. Okay, what do you guys think? How many of you guys think they're gonna get brighter but don't change at all? They're just gonna make it. It's just gonna, since you're moving it closer to light, these little fringes will just get brighter. Okay. How many of you guys think it will get brighter and it will get closer together? Okay. Okay. So those of you guys thought that is correct. So why is that, right? Anyone wants to tell me why they figure that out? How they figure that out? Right. Right. Even these are coming out at constant angle, right? If you cut this off right here, right, the fringes will actually be closer together because these angles are coming out, and then as you go out more and more, they spread out further, right? Okay. Right. So there's gonna depend on these fringes is gonna depend on the distance. Go away. Why are you doing that? Right. The distance between the slit and the screen, right? Basically, we're going to call that length L, okay? Capital L. Let's see. Okay. So let's try to figure out how we can analyze this so we can do a little bit of, math with it so we can actually predict what's going on, right? So what I'm going to do is I'm going to draw the double slit as this, right? There's two little gaps there, right? And the screen is over here, right? That's my little screen, okay? Remember I defined this to be some length L, okay? What I'm gonna do, instead of drawing a bunch of waves, I'm just gonna draw basically two crest lines of the waves so that I can actually just do some geometry with it, right? Let's say I'm at some point, so the midpoint here is this, right? This is the halfway point, okay? Let's say I'm looking at the light at some point, basically y above the midway point, okay? What I'm going to see there is I'm going to see one wave, sets of waves coming out from this point, and then another sets of wave coming out from this point, right? Okay, right? And the thing we care about is the difference in the distance that they have to travel, right? Do you guys remember why I care about that? Right, if we go back up to here, right? The difference in distance that the wave has to travel determines whether or not you're going to get destructive or constructive, right? And we're trying to figure out whether we're going to get constructive interference there or destructive interference there, right? Right? So the orange light is going to travel this length, right? But the blue light is going to travel that length plus a little bit, right? It has to travel a little bit longer, right? So what we're going to do is going to do a little trigonometry there, right? Draw triangles, right? So if we do this, right, these two lengths are the same now, right? Okay, and this length here is our delta r, right? That's the difference in distance that the light has to travel in order to reach the screen, okay? Well, so how do we figure that out, okay? Okay, so if we have on this side here, these two angles relative to the horizontal, right? I'm just going to do more dotted lines here. Dotted lines, dotted lines. This theta and this theta, they're approximately the same, okay? Because they look a little bit different, but they're approximately the same. So therefore, what we can do is that, well, the angle here is also going to be theta, okay? Right? So we have a little triangle here. I'm going to bring the triangle out. Okay, we have a little triangle here, right? Right. This is delta r, the thing we're interested in. This angle is theta. This distance here, right, is the separation distance between the slits. We're going to call that little d. Okay, that's how far the slits are separated from each other, right? In order to figure out what delta r is, right, which one is this is the opposite, right? This is the adjacent, and this is the hypotenuse, right? In order to figure out what delta r is, right, we know that sine of theta is going to be delta r over d, right? In other words, delta r is actually d times sine theta. Okay, make sense? All right. Okay. Ooh, there's a lot of space here. Yeah. Okay. In fact, oh, that's why I have left a lot of space. I'm supposed to make a much bigger drawing. In fact, right, since y is just some variables that can be going up and down, right, this delta r can be at, can be different, right? If I redraw this same experiment, yeah, move down. I think I'm having all the simulation running, that's why the computer is being slow, right? If I redraw this, right, where the orange, let's say, is at a much steeper angle, the blue here, right? Right? This delta r is going to be different, right? So at every y value, we're going to have a different delta r, right? So what we're going to do is we're going to label them, okay? Delta r, and it's going to be slightly different for each of this angle, but the distance d between the slit doesn't change, right? So it's d times sine of theta m, okay? And m is just some index, okay? Going to be 0, 1, 2, 3, dot, dot, dot. Okay, some integer that you just count up, okay? Okay, just different angles. Okay, I think my computer is struggling. Okay, right, and that's where equation 33.3 comes from, where this difference in how far the light has to travel is just the separation distance between the slits, okay, times sine of theta m, okay? And remember, when we have integer multiples of wavelengths as the difference in the distance, this is when we have constructive interference, right? Okay. And therefore, now what we can do is that, well, we can solve this equation here for basically theta m, okay? What we're going to do is we're going to do a small angle approximation where we're thinking, oh, sine of theta is approximately theta, right? For a small angle, that's accurate, okay? So therefore, this is actually not accurate calculation at big angles like this, but if you're close to the first few fringes, this is a pretty accurate approximation, okay? So in order to solve this equation here, then we have d equals to theta m equals to m lambda, right? And then solving this for theta m, you just get that is going to be m times lambda divided by d, okay? Okay, and these are the angles that's going to give you the bright fringes because we impose the equation that, oh, it has to be bright fringes, right? So it has to be constructive interference, okay? Right? So that gets us the angle. Ooh, there's too many things going on here, right? But what if we want the position? We want to figure out how in y, you know, in the vertical axis y, how far up they are, right? So once again, we're just going to do a little trigonometry, right? Where we have the slits there, right? And then we have the one slit creating the light over here, and then the other slit creating light over here, okay? So we figure out what theta is, okay? If we want to convert that to basically y, right, this will be y sub m. So for every angle of m, you're going to have a different position in m, right? Right. So, and since the distance between the the screen and the slits is this length L that we just defined, right? We can do a little bit more trigonometry. Is that well, what we can say is that, well, tangent of theta m should be opposite over the adjacent, right? So this is y sub m divided by L, okay? Once again, we're going to do a little small angle approximation where we're going to say that, well, tangent of m is approximately just theta m, okay? And then we do this little approximation here, okay? And we can calculate what y sub m is. Y sub m is just theta sub m times L. And theta sub m, right, is this equation up here. So it's just m lambda L divided by d, okay? So you can actually figure out exactly where the bright fringes are because that's where you will get constructive interference, okay? Any questions about this? A little small angle approximation that we play with all the time, right? You could solve this without this small angle approximation. It just turns into these inverse tangent functions, that's all. And this is just much easier to deal with for now, okay? Okay. All right, so you can also predict the distance between the fringes, right? Because we have this equation here, right, for, that's a weird m. For every m, right, let's say m is equal to 0, you put in 0 here, right? That means it's just going to be horizontal, right? But the m can be 1, 2, or 3, right? If you want to predict the spacing between the fringes, right? Let's go back up to the picture here, right? So this is y sub m, and this, and then let's say we want to predict where the next bright fringe is going to be, right? We're going to call this next one y of m plus 1, right? Because that's the next index over, okay? So if we want to figure out the distance between these 2 points, these 2 bright fringes, we just need to calculate, you know, what is y sub m plus 1 and subtract it from y sub m, right? If you want to find the difference in these positions, you just subtract them, right? So you plug in the formula for y sub m plus 1, and then you subtract it with the formula for y sub m. Interestingly, what happened is that the m actually cancel each other out, well, subtract each other out. So let me just show that to you guys real quick. So m plus l minus 1, right, over d, m lambda l over d, right? You can factor out, oops, this lambda. If I did the math correctly, then I can show you guys more easily, right? You can factor out this lambda times l over d, right? Because they're in common on both terms, right? So what's left over inside is actually m plus 1 minus m, right? The m's actually subtract each other out. So all you're left with is just lambda L over D, okay? So the fringes are always going to be whatever the wavelength is multiplied by the distance to the screen divided by the distance between the slits, okay? Right? We can repeat the same derivation if we want to find the dark fringes, meaning the dark spots where we get destructive interference, right? Remember the condition for destructive interference is that they have to be 1/2 of a wavelength plus some integer apart, okay? This m plus 1/2 allows you to basically just, you know, it's 1/2 of a wavelength, 2/3 of a wavelength, whatever is after 3/3, three halves of a wavelength, 5 halves, you know, and so on like that, okay? All right. So let's do a quick example of this, okay? All right, see how these are used, okay? In some double slit experiments, okay, we have some pattern on the screen that's 1 meter away, okay? So let's start doing the setup by doing the drawing, right? We have some double slit experiment, and then the screen is 1 meter away, okay? The 2 slits are spaced 0.3 millimeters apart, so that's actually the distance D, right? That's 0.30 millimeter. This is 1 meter, okay? The 10 fringes spans a distance of 1.7 centimeters, so that means, so there's 10 fringes here, but they are 1.7 centimeters apart, okay? This is actually what variable? This is delta y times what? If there's 10 fringes that spans that, right? How many, so we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 fringes here. That's that far apart. So that's delta y times what? Times 10, right? This is actually 10 times that, okay? Okay. Be careful. Yes. I think I just figured out what the problem is, right? So the spacing between 10 fringes is actually 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So it's actually 9 times that. Yeah. Okay. Because when you count, right, you also count the endpoints. Okay. All right. So the question is, what is the wavelength of the light? Okay. So we can use these bright fringe equation that we just did, right? So we know that, well, delta y is going to be this. Okay. Lambda times L divided by D. Come on. Delta y is lambda times L divided by D. And 9 times that will just be 9 times that, right? Okay? Okay. So let's call this variable, you know, y9 or something like that. Okay? Okay, so that's equal to y9. Okay? Okay, so we know what this is. We know the distance between the slits. We know the distance there. We know what 9 is, so we can actually calculate what the wavelength is. Okay, so the wavelength is actually going to be y9 times d divided by L divided by 9, right? So Y9 was 1.7 centimeters, so 1.7 times 10 to the minus 2 meters. So all of this has to be in meters. D is 0.3 centimeters times 10 to the negative 3 meters. Okay.
Millimeters?
Yeah, it's in millimeters, so I just convert from meters to millimeters by just taking it to 10 to the negative 3, right? Okay, the distance to the screen is just 1 meter, right? And then we have to multiply by this number 9. If I compute that, hopefully we get something that's sensible. 1.7 e to the negative 2 times 0.3 e to the negative 3 divided by 9. Okay, I got a wavelength that's 5.67 times 10 to the negative 7 meter. Okay, and to check whether or not this is sensible, right, we know that the light, right, visible light especially, right, is somewhere between 400 nanometer to about 600 nanometers, right? So hopefully this is something that we can actually see. So if I move this decimal over to the right twice, right, that means 567. If I move this to the right, I have to reduce this power by negative 2. Okay, that means this is actually 567 nanometers. Okay, so these nanometers are going to come up all the time, okay, when we're dealing with light, because that's actually usually the wavelengths of light, right? Notice that it is somewhere between 400 and 600. Okay. All right. So yeah, let's do another. Any questions about the example before I move on to the stop to think thing? Sort of also neat. Okay. So let's do the second stop to think thing, where let's say we have some light with wavelength lambda 1, okay, it illuminates some double slit, okay, and the interference pattern is observed behind it, okay, but then the wavelengths change to lambda 2, the fringes got closer together, okay. Did I increase the wavelength or decrease the wavelength? Is lambda 2 larger or smaller than lambda 1? Okay. Okay, remember that delta y is just going to be lambda L divided by D. Okay. So if the spacing between the fringes uh, decrease, right, did the wavelength go up or down? How does the spacing depend on the wavelength? Is proportionally or inversely proportional? Proportionally, right? So if the spacing went up, the wavelength also has to go up, right? Yeah, because we kept L and D the same, right? We didn't move the experiment, okay? So therefore, right, since the fringes move closer together, delta y got smaller, so also the wavelength got smaller, right? So therefore, wavelength number 2 should be smaller than wavelength number 1, right? Okay. All right. Any questions about that? All right. Now what we're going to do is we're going to kind of calculate the intensity. Remember, intensity is basically how much power per area that you're delivering this electromagnetic energy to, okay? And back in chapter 17, once again, right, what we're going to have happen is that, let's say you have two waves that are partially constructively interfering sometimes, and then destructively interfering sometime where the zeros are. And what happened is that depending on the phase angle between the two, so how aligned they are with each other, right, you're going to either get some combination of the two, or you're going to get more destructive interference, okay? And we're not going to go through all that math from chapter 17 again, but I just want to show you where these equations are from chapter 17 in case you want to look them up yourself, right? When we have two different waves, right, that are at some phase, meaning they have a different distance, they have a delta r between them, what happened is that you can do a bunch of trigonometry math where what happened is that, let's see, right, the amplitude of the resultant wave going to depend on 2 times the original amplitude Okay, so this little a is not a different a. This is the original amplitude. Okay, cosine of the difference in the phase angle between the two divided by 2. Okay, all that trigonometry just kind of gets you to this point. So if you want to look that up from chapter 17, please feel free to do that. Okay, since we're treating our electromagnetic wave as a wave right now, so we can apply exactly the same equation here. Instead of the amplitude of oscillation, which we dealt with in chapter 17, right, we're dealing with the magnitude of the electric field of the electromagnetic wave, right? Ugh, go up. It's just being really sticky. Okay, right? So instead of the lowercase a, right, we're going to use a lowercase e. This is the electric field amplitude. Amplitude of the individual waves, okay? Individual waves, okay? Don't blame me for using the lowercase e, because that looks like electric charge to me also, but the book decided to use this notation, right? Okay, so if we want to find the phase difference, right, we're interested in trying to figure this out between the two slits, okay? What will happen is that basically what you will see is that the phase difference, let's do this drawing real quick. We've got 4 minutes left, right? Right, the phase difference between them, right? Because we figure out what this delta R is, right? This delta R, right, is going to tell us the phase difference if we multiply by 2 pi divided by the wavelength of the light. Okay? And remember that this delta R, right, we found that it's just going to be the distance between the two slits times sine of theta. Okay? What we're going to do is doing a different approximation where we're going to replace delta R with this. Instead of approximating sine of theta as just theta, right, we're going to approximate it as tangent of theta. Okay, the two functions are pretty similar to each other when we're at small angle. Okay. Okay. Right. The reason for this is that tangent of theta, remember this is where the screen is, right? Tangent of theta is actually y sub m divided by L, right? So if we place tangent of theta with y sub m divided by L, right? They didn't put an m there. Okay, we can actually have this kind of function that doesn't have any trig function in it. Okay, and you can plug this in, right? 2 pi times the separation distance between the slits divided by the wavelength divided by the distance to the screen times the y position of this, right? We can plug that in as delta phi. Okay. Okay. And then once again in chapter 31 we learned that, right, intensity of light is actually going to be this 1/2 the speed of light times epsilon naught times the electric field square, right? What the book did is basically they lumped this into this constant called capital C. Okay, so the intensity of light is just basically whatever this constant is, 1/2 times the speed of light times epsilon naught times the electric field square, right? So if we plug this in here, what happened is that we're just going to have a bunch of constants here. So this is not the charge of the electron. This is the amplitude of the electric field for the one wave, right? Okay. And then you have to multiply this by cosine square because we figure out that, you know, this gets squared because of the electric field square. Okay. So to calculate the intensity in the double slit experiment, since we're going to have two different sources, okay, this is going to be 4 times whatever the intensity is at the center, okay, right, right. This I1, right, stands for the intensity at the center, okay. At, we'll what's known as the central bright spot. Okay, and then it just has this cosine square stuff attached to them. Okay. Okay. And I'm not gonna go do the other one. Okay. Okay. So that's all. I think we're gonna. Oh, let me just show you what this looks like. Okay. So, what this looks like is that at right in front of the slits, right? If you just go straight horizontally out, you'll get the brightest spot there. Okay. As you move away from it, the intensity is gonna go down as cosine square of that function we just derived. Okay. Okay. So the intensity just kind of goes down as we go upward. Okay. Until you basically can't see it anymore. Okay. So that's all I have time for today. So tomorrow I'll maybe have a little laser and show you guys how this looks like.